Good morning, I'm Andrew, and I work as a kernel developer at IBM, who doesn't take any responsibility for all the mistakes I'm about to make in this presentation. Today I'm going to be talking about fuzzing the kernel on the Power architecture using syzkaller. So first we'll start off with a bit of background about syzkaller, what it is, and why it's useful for us to be using it, and then I'll be going through a bit of what we did to get it running on the Power architecture in our lab. I should caution up front, this talk is not going to be exhaustive. There are various sagas that I have omitted in the interests of time, but hopefully this should give you a bit of an idea of what was involved, at least for one architecture, in taking syzkaller and getting it running in a lab environment so that we could start finding some bugs. So first up, what's fuzzing? I suspect quite a few of you in the audience, given that you have self-selected to come to this talk, probably know what fuzzing is. But for those of you who don't, fuzzing is a fairly old idea. It's been around for a few decades at this point. It's still a great way to find all sorts of bugs in various types of software. You test a program in an automated way by throwing randomized, mutated, invalid inputs at a program. And inputs can mean various different things depending on what type of program or library it is that you're looking at, and you just keep generating these inputs and throwing it at the program that you're trying to test until it crashes or reaches some kind of unexpected failure state that you can detect, and that's usually a good sign that you've got a bug. And you might ask, well, what would you expect if you throw an invalid input at a program? Well, typically you would expect the program to crash gracefully, to give you an error message that says, you've passed me an invalid file, I can't read it, not to segfault, which implies that it's doing something wrong. So if you're a user space developer who's trying to do some basic fuzzing of an application or a library that takes input in a fairly standard way, like, for example, you're loading a file from disk. There are a bunch of generalized fuzzing engines that are out there, open source, that you can make use of fairly easily. Probably the most famous and well-known one is AFL, American Fuzzy Lop, which has, that project is defunct now, but it's got some spin-offs like AFL++ that are still maintained. So for example, you have a library, a user space library that takes a PNG file and loads it and does some processing on that. Image libraries are a classic target for fuzzing because they're often parsing an extremely complex file format that's easy to get wrong, and they're often written in the world's greatest programming language, C, which definitely provides you with no opportunities to shoot yourself in the foot with memory corruption bugs. And of course, something like libpng or whatever, often embedded in applications like web browsers, which are considered high-value targets from a security point of view and have a lot of users. So fuzzing is considered a pretty high-value thing to do. So in a situation like that, what you would do is you'd write a short wrapper program that takes a file path, loads the file, calls the functions in the library that you're testing, and then you'd go and run, say, AFL++ at it, and it would start generating random files and getting the coverage information from that and generating new inputs until it hits some crashes and sit back and wait for crashes to emerge. And then there's some more advanced stuff you can do to tweak it and, if you want better performance. However, sometimes you want to run your own fuzzer. So that could be you want to test a particular interface in a way that understands the domain-specific details and does things a bit more intelligently than just randomly mutating stuff and running purely off a coverage-guided fuzzing algorithm for a general application. Or perhaps your fuzzing target is the Linux kernel, in which case your fuzzing input is takes the form of not a file that you're generating, but a program that you have to run on a computer that's going to crash if you successfully fuzz it. So this is a little bit of a challenge. And so what we're going to look at today is syzkaller, which is a bespoke fuzzer focused on the kernel system call interface. So what's syzkaller? It originated at Google. It's an open source project, but they're kind enough to fund a few very smart people to work on it. It's written in Go, which is probably not all that surprising because Google. From the README, syzkaller is an unsupervised, coverage-guided kernel fuzzer for Linux and for a bunch of other operating systems, as you can see, the BSDs and even Windows and some other options. So let's dissect each part of that in a bit more detail. We know what a fuzzer is. What's an unsupervised coverage-guided fuzzer, kernel fuzzer? Well, it's a fuzzer that runs automatically using compiler coverage instrumentation to figure out what code paths are being executed by a particular fuzz input, and then generating new inputs with the goal of exploring as many different code paths as possible and exercising different paths. So coverage-guided fuzzing uses instrumentation that's added by the compiler. Basically, when the compiler adds a function call at the start and end of each basic block of straight line code with no conditionals in it. And then you can use that information. So that basically logs what path the code takes as it's executing, and we can retrieve that data and feed that into the fuzzing algorithm. Now, I should caution, I actually haven't touched the core syzkaller fuzzing algorithm at all in this work, so I don't really know how it works at all. So I'm not going to talk about it. But the main thing you need to know is that coverage-guided fuzzing is probably the single biggest innovation in fuzzing since fuzzing became a thing. It increases the efficiency of the process hugely. Syzkaller is a kernel fuzzer, so it targets kernel interfaces, such as system calls. Why do we care about fuzzing the kernel? You can probably guess why. It's the kernel. If it crashes, your whole system crashes. If it has a security vulnerability, the attacker takes over your whole machine. And it's, again, written in the world's greatest programming language, C, which has no memory corruption bugs. Sorry, it's written in C and Rust now, I should say. Rewrite everything in Rust, it's great. The other thing about the kernel is that it has quite a few complex attack surfaces. So we've got the system call interface, we've got ioctls, we've got USB, we've got networking, file systems. File systems can be, corrupted when there's a power outage or something, or they can come from untrusted sources, like someone's USB stick that gets plugged in, automatically mounted by systems that automatically mount things for some reason. You've got eBPF, which is a way for user space to run code safely in the kernel, or sometimes not so safely when it turns out there's bugs. You've got KVM virtualization, where you've got the guest kernels having to interact with the host kernels to do certain things. And probably a bunch of things that I've forgotten to mention. So syzkaller focuses on syscalls. It also touches on, ioctl is a syscall. It's a bit of a subset of an interface on its own. It also does some fuzzing of the USB interfaces and networking, KVM, a little bit of file systems, just as part of the syscall fuzzing. And it's not the first attempt at fuzzing the kernel. People have been trying this for a while, but the major thing that distinguishes it from its predecessors, such as Trinity, is the fact that it uses modern coverage-guided techniques. And this has made it ridiculously successful at finding bugs. It has reported thousands of bugs to the mailing list, much to the annoyance of some kernel maintainers. So as I said, I'm not going to go into the details of how the syzkaller fuzzing engine works, but what I will discuss is just the overall structure of the components, the various components of the syzkaller stack, and what's necessary for deploying it on Power. So I'm going to show a few diagrams which are shamelessly stolen from the syzkaller documentation. I apologize, they're a little bit low res, but that's how they are in the documentation. So this diagram, it shows, you can see syzmanager, syzfuzzer, and syzexecutor. So the yellow box here is the machine where the kernel, that is running the kernel that is being fuzzed. So this machine is almost always a virtual machine, which, for the obvious reason that you want to be able to spin them up quickly, monitor them, and then kill them when they crash, because you're running a fuzzer on it. So inside that VM, we have a program called syzfuzzer. So that's responsible for generating the fuzz inputs. The fuzz inputs are a sequence of syscalls that it wants to make. And it monitors the kernel's coverage information, which is exposed through sysfs. It then sends the fuzz inputs to syzexecutor, which then proceeds to make a bunch of syscalls, and we see if it crashes. Outside the VM, we have syzmanager, and syzmanager is responsible for booting up the VMs, monitoring them from the outside, tearing them down when they die, and capturing the reports, the errors that it sees on the VM's console when we do hit a crash. syzmanager has a web interface that lets the user see the reports, and also importantly for our situation, it can run on a separate machine from the fuzzer itself, and that machine does not have to be the same architecture. So you can have a syzmanager running on x86 and your VMs running PowerPC or ARM or whatever else. So this is what the web interface for a syzmanager looks like. It gives you a bit of information about how the fuzzing is going, and then it shows you a list of crashes, including the crashes for which it's got a reproducer program that you might be able to use to recreate the bug and help to debug it. If you click on one of the bugs, then you get to see all the occurrences where it has hit that particular error, that particular type of crash. And from that, you can get the console log and the extracted error message for your debugging perusal. So, for example, I click report on this bug, you'll get something like this. This is a current PowerPC kernel bug, which I started looking at and have not yet fixed. I've got a patch sitting in a branch somewhere that I have not yet, I think it compiles, I haven't tested it. But, you know, so this particular bug was, the kernel was built with preemption enabled, which is not actually the usual setup for PowerPC server builds, but it's something that we do for the syzkaller debug kernel builds, because it reveals a bunch of bugs. And we've hit a function here which is being called in a preemptible context, so preemption is enabled, and it's calling the function SMP processor ID to get the ID of the current CPU that it's running on. This is not actually permitted when you've got preemption, kernel preemption enabled, because you can get the processor ID, and then the scheduler can go and take you, can preempt you, and then move you off to a different CPU, and by the time you resume and actually make use of that processor ID, you're running on a different CPU thread, and you're probably not doing what you thought you were doing. So there's a debugging option that you can switch on that will give you an error whenever you call SMP processor ID in a preemptible context. So it prints a warning, and we have panic on warn set, so it actually causes a kernel panic on any warning, and syzkaller picks this up and reports this. I will fix this bug soon when I get back to work, I promise. So a single instance of syzmanager runs multiple fuzzing VMs with a single kernel binary, and it compiled with a single configuration. This diagram shows the broader context of what happens when you want to build multiple kernels with multiple configurations and run them potentially on multiple platforms. There's another tool called syzkaller. You can see that it's the box right in the middle there. It fetches kernel sources from Git, compiles them, and then sets up multiple sys managers, potentially with different configs, and creates a disk image for each sys manager with the new kernel installed so that it can deploy VMs. It can then take all of those reports and collate them and ship them off to the external dashboard. The dashboard is a Google App Engine application, which I'll talk about in a moment. So this is the public syzkaller dashboard of Google's instances that they run in their cloud. You can see it at syzkaller.appspot.com. This generates all the emails you see on the mailing list with syzkaller bug reports. It's got a ton of features. It's extremely cool. But I'm not going to go too much into detail right now. So how does syzkaller know how to generate a fuzz input? It needs some manually written descriptions of each possible system call. That's done in a text format like this. This is a simple example from the documentation. Note here that the parameters and the return values have types that indicate that can indicate the types of resources that they're using, not just int or string or whatever. But we have open. It takes a file name of type file and returns a file descriptor. We've got read that takes a file descriptor of type file descriptor, and that helps syzkaller to fuzz things in a sensible fashion. We don't want to just make syscalls to we don't want to just call read with random file descriptors which are random ints. That's not going to be a particularly interesting, unless you've failed to validate that the file descriptor is valid. But that's kind of a basic thing to get wrong, so it doesn't get you very far. Instead, it creates valid file descriptors by calling open, getting a file descriptor, calling read with that file descriptor. And after you change these descriptions, there's some internal tooling to turn that into magic Go code and to extract all the relevant constants you need from the kernel source. This is a program written by the fuzzer, again from the documentation. As you can see, it's just a simple sequence of syscalls. This gets passed to sysexecutor. Sanitizers. So to get the most out of any fuzzer on a modern C program, you want to enable sanitizers. So these are compiler features implemented in recent versions of Clang, GCC, and so on. They compile your code with runtime instrumentation that helps you to shoot yourself in the foot a bit less. It will print a warning when you do things like access invalid memory or have data races or undefined behavior, everyone's favorite C feature. Those of you who are at Paul McKenney's talk at this conference will understand the importance of trying to catch near misses rather than just the errors that actually cause other, user visible errors. These sanitizers will help you catch situations which don't necessarily cause failures in real life usually, which is really, really great. For a normal user space program, enabling sanitizers is usually just a matter of adding a compiler option and linking it against the runtime library for that sanitizer. But we're running in the kernel, and we're a bit special. You have to do a lot more care around memory management, and you've got a lot of architecture-specific fun, and you can't link against the standard runtime libraries that they ship. So there's in-kernel implementations for all of this stuff. We've got the address sanitizer. It finds memory errors like use after freeze, buffer overflows. We've got KMSAN, the kernel memory sanitizer. Go back in time to Nick's talk on Tuesday, or watch the video. Finds even more memory errors. It just runs slower. KCSAN helps detect data races. UBSAN for undefined behavior, and we've got a few other things like KFence, which we don't really care about as much when we're running KASAN and KMSAN, which are better memory sanitizers. Yeah, we're currently on our power setup. We're using KASAN, KCSAN, and UBSAN. KMSAN will happen any day now once we finish Nick's patches to get that enabled on power. So now we know what syzkaller is. I'm trying to get it to run on the power architecture. What's the power architecture? Some of you may know it better, and indeed it's still called in an awful lot of places PowerPC. Technically, that only refers to a certain subset of the architecture historically, but we kind of use that term interchangeably. It's a RISC architecture that originated out of IBM in the late 1980s, early 1990s. It was adopted by the AIM Alliance, Apple, IBM, and Motorola. as the future of personal computing. It became the successor of the Motorola 68K chips that were used in the Mac. So my own personal journey with PowerPC started as a 6-year-old, thanks to the New South Wales Department of Education and Training at Hastings Public School in Port Macquarie, buying a bunch of iMacs with the PowerPC G3. Mac OS 9, it was not a great time. Cooperative multitasking, many people who don't pay attention to enterprise computing are under the misapprehension that when Apple switched away to x86 in 2005 or whenever it was, that PowerPC disappeared. But no, IBM still makes servers. This is an E1080. It runs with our current generation of Power 10 processors. It's built for scale-up enterprise stuff, SAP HANA, in-memory databases, that kind of thing, where you need a lot of memory I/O and a lot of grunt. And traditionally, Power servers ran IBM's proprietary operating systems, AIX, IBM I, but Linux is now an extremely popular option. And we wanted to get syzkaller running on Power in order to exercise and find bugs in the architecture-specific support code that can't be tested on Google's farm of x86 machines. So what did we need to do to get it running on Power? I'll go through what did we change in the kernel itself, what did we change in syzkaller, and how we deployed it on our lab network. I'm not going to cover absolutely everything, as I said. This should give you a relatively good overview of the broad story. So in the kernel, we had to enable kcov coverage guidance support. In syzkaller, updating the syscall descriptions for the to add the new architecture. Conveniently, the Google upstream devs did that for us, so I actually don't know how to do that, and I'm not going to talk about it. But we also had to change a few things to ensure that architecture-specific details in like kernel error reports, CPU information got parsed correctly. We had to add some additional kernel configurations for it to build with, and do a few changes in the disk image build scripts that it uses to put together disk images to send to the VMs. I'll touch on instruction level fuzzing. It's not an area I know very much about, but one of my former colleagues did some work in that area. And then finally, we had to figure out how to actually get it running on how to manage VMs on Power hardware and deploy it on our lab network. So syzkaller is a coverage-guided fuzzer. For this to work, we need kcov, which is the kernel coverage sanitizer. It causes the kernel to be compiled with the compiler coverage instrumentation, and it provides the runtime support in kernel space that is necessary for that to work. It exposes that coverage data to user space in sysfs. Sysfuzzer can then read it and feed it back into the fuzzing process. When we started working on this, we didn't have kcov support enabled on PowerPC, so that was the first thing that we needed to figure out. We went to Arch PowerPC kconfig and added the line select Arch has kcov, and that was in fact most of the, that's most of the work done thanks to other people, but not all of it. There are various bits of code where we can't add coverage instrumentation. They do weird kernel things like running super early in boot or running during kexec and doing interesting memory management stuff and assembly shenanigans. So we had to figure those out and add compiler options to in the makefile to turn off kcov on those things. That was mostly a process of trial and error. We also had one piece of code where we had to rework the logic because there was a compiler warning that was a false positive that incorrectly got triggered only if you compiled with coverage sanitization enabled. I still don't understand why, but we just rewrote the function to look nicer anyway, and it went away. Now that we have kcov, we can run things, and then we can get an awful lot of messages in syzkaller saying, report corrupted, because it can't understand them. So sysmanager needs to be able to understand the errors printed on the console so that it can figure out what happened, give the bug report a sensible title, and deduplicate the errors that it hits multiple times, which is the most important thing. And unfortunately for us, many kernel error messages are printed slightly differently on different architectures because they're printed in architecture code. And most significantly, stack traces, which it uses to figure out what function name is responsible for the particular crash and put that in the report title. So on the left here is a PowerPC stack trace. On the right is an x86 stack trace. You can see, for example, we print the addresses a bit differently. x86 puts angle brackets around the addresses for reasons I don't get. PowerPC prints both the stack pointer and the instruction pointer. So there's a few differences here that, that syzkaller needs to be aware of. How does syzkaller make sense of these traces? That's right, you guessed it, a 2,500 line Go file that contains, like, probably more than half of that is just regexes. Quality regexes like these that look beautiful. There are some characters somewhere on this slide that are possibly my fault, and I can't point to which ones they are. There were a few other aspects of error message regexing I also had to adapt to get it to skip over certain functions that we use on PowerPC and blah, blah, blah. But I really don't want to think anymore about that 2,500 line regex file, so we're going to move on. Proc CPU info. Looks at that to gather data about the machine the fuzz is running on. It's architecture specific, surprise, surprise, different CPUs. So previously it checked for vendor model and flags fields, and it assumed that every architecture it ran on had an equivalent field. We don't have an equivalent of the flags field. We've got a few other different things. So I had to rewrite that code to use an architecture specific list of metadata about the CPU. Kernel configuration. So syzci needs to be able to compile kernels with all the right kernel configuration options enabled. And in order to do this, it has a tool called syzkaller. Syzkaller takes in a gigantic set of YAML files which describe all of the options that we want to have enabled in particular configurations. It lets you define different features as different sets of features, and then sort of combine those together, compose them into an overall configuration for a particular platform. So we had to define some PowerPC configurations that use the right architecture-specific options, and disabled a bunch of options for drivers that we happen to know are broken and we don't have time to fix right now, and certain drivers that compile on x86 but they don't compile on Power because they don't have the right prerequisites on Power, that kind of thing. And then we had to trial and error our way through certain other stuff to work around issues in our deployment, which I won't get too deep in the weeds on that. It took a bit of experimentation, and honestly, I don't quite understand the syzkaller YAML language completely at this point. But here's some of what we had to do. So you can see you can specify different options and say N if you want to guarantee that they're turned off, or you can say override if you want them turned on, but overriding an option in another part of the YAML. Yeah, we had to turn on the ISO 9660 driver for reasons related to our cloud platform, and switch off various debug options that cause it to crash on boot, or spit out warnings on boot deliberately. That doesn't work with syzkaller. And then there were a few other places in the code where we had to define the right build behavior for when you compile a PPC64 little endian target. So for example here, different architectures, we choose to use different kernel binaries. This does not actually match what's currently upstream, but we're currently using the VM Linux file from the root of the build directory for PPC. I think upstream it uses, arch PowerPC boot zimage.p series, but we had to change that. So once we've compiled the kernel, we need to create a disk image that has the kernel installed that we can then pass to the VM. To do this, there's a shell script you could use to build a minimal Debian distro using debootstrap. I had to make a few fixes in there to fix some bugs with what happens when you want to cross debootstrap a foreign architecture, because I do that a lot, running an x86 machine and wanting to build a Power image. And then there's another shell script which gets invoked by syzci itself once it compiles the kernel, it takes that miniature distro and creates a disk image with the kernel installed, ready to boot. So the main difference between x86 and the PPC64LE target is partitioning and bootloader configuration. This is one of my favorite, most aesthetically pleasing lines of code I've ever written. The fdisk command prompt is a fantastic programmatic method for partitioning a disk image. You can see this is extremely reliable and will never break. So, for example, the difference here between the PPC option and the AMD 64 case is that we have to create a PowerPC reference platform boot partition. So that serves a similar purpose for Power machines as the EFI system partition does on x86 or other platforms. It's a separate partition onto which you can throw your bootloader. And there's a few other things I had to do here, which I'm not going to get into, but I thought this line particularly was very aesthetically pleasing, so I should, show it to the world. Instruction fuzzing. So I'm only going to talk about this briefly because I'm not overly familiar with this aspect of syzkaller. Full credit for all of the PowerPC instruction fuzzing work goes to my former colleague, Alexei Kardashevsky, who is smarter than me. The purpose of instruction fuzzing, it generates and mutates sequences of machine code instructions, and it can use that to create programs that we can run. I believe it's particularly useful for testing the KVM pathways, because syzkaller can create KVM guests, which are often nested KVM guests, because you're often running syzfuzzer within KVM to begin with, and then it can execute stuff inside that guest, and then that will, of course, cause things to happen which require the host to intervene and do something, and that exercises provides a bit more coverage of the KVM pathways. I believe the only architectures that have support in the syzkaller ifuzz package are currently x86 and PowerPC. So if you want to go do it for ARM, then I'm sure they would love that. And the way that we did this, Alexei wrote a very cursed Python script. What it does is it takes a PDF of the Power 9 ISA and then runs it through PDF to text and parses that somehow. I do not want to look at that code, and turns that into Go code. So with all this structure information that looks like this, yeah. So this all just describes like a particular instruction, what its opcode is, and what the various fields are for, like, the target register and the source registers, and that kind of thing. Again, allowing the instruction fuzzing code to be a bit smarter about the way it works. So after we get the disk image, we have to boot a VM. So the first thing that we did was we grabbed some spare Power 8 and Power 9 machines that were lying around our Canberra machine room, and we got them running Linux bare metal. These were open power machines, which tend to operate in bare metal mode. So you're running Linux bare metal and using it as a KVM hypervisor and creating KVM guests inside that. And we use QEMU to do that. Syzkaller supports multiple backends for creating VMs, and you can specify which one you want in the sysmanager configuration file. Google Compute Engine, obviously, is what Google uses in their cloud. They trust syzkaller to not bring down their cloud. And QEMU running on the same machine where sysmanager runs is also supported. So we did that. That did require a few changes to make sure that it was adding the right QEMU command line options to make things work, because that differs between architectures. So our setup had a few reliability and infrastructure issues at that point. We were running it fairly inconsistently. just, when we got the opportunity, and then someone wanted to, take a machine for another purpose and tell us to stop syzkaller and whatever. But we did manage to find a bunch of bugs with that. So firstly, as I mentioned earlier, when you wire up kcov, you have to exclude certain areas where the kernel does fun kernel stuff. And we found more of those areas. So we had to send follow-up patches to fix the initial kcov patches that sent. We also found that the KVM host was actually crashing or hanging a bit. That's quite bad. You shouldn't be able to crash a virtualization host from an untrusted guest. We think that was mostly exposing a bunch of race conditions and similar issues that happen when you really stress test the system hard. It turns out that syzkaller is actually a really great system stress test. But we had to fix those. So Paul McKerris did a lot of that work, who some of you may know. We found some bugs in the Power implementation of kernel user space access prevention, which is a hardening feature that helps stop the kernel from incorrectly accessing user space memory. So that's kind of awkward to have to find bugs in your own security hardening features, but important that we do that. And we found a few other things, which I won't get into, but as you can see, we detected a few bugs, some of them quite important. Once we got syzkaller working using QEMU on KVM to create the fuzzing VMs, we then moved on to looking at IBM's enterprise hypervisor, Power VM. And the main reason we wanted to do this was that Power VM is the current focus for the current generation of Power 10 hardware. It's the only option that's officially supported for our enterprise users. And so that's the environment that our customers are going to be running in. We got ourselves a shiny Power 10 box in IBM's lab in Austin, and taught ourselves enough systems administration skills to figure out how the Power Enterprise hypervisor platform works. So unlike KVM, which is a subsystem that runs within Linux, within a general purpose OS, Power VM is a type 1 hypervisor. It's just a pure hypervisor. It doesn't do anything other than manage guest operating systems underneath it. So you can't just like SSH in and get a Unix command line or anything. It runs Linux and AIX and IBM I as the guests underneath it. Use a separate machine, the hardware management console, to manage. That talks to Power VM and manages the machine and its VMs and provides you with a nice web interface. And you've also got the virtual I/O server. So that's actually a dedicated VM on the system that is responsible for managing all the disk and network I/O on behalf of the other VMs. So Google runs its Syzbot setup publicly using Google Compute Engine. And for our private Power VM machine, we use Power VC, which is IBM's private cloud solution for enterprise power. Power VC is a customized version of OpenStack, basically. It has a back end that can talk to the HMC and the BIOS to set up VMs and set up storage and network and that kind of thing. And it can also manage the usual stuff like assigning IP addresses and whatever. It's OpenStack based, so we can use the OpenStack API for the most part. It does have a few extensions that aren't in upstream OpenStack. It doesn't support every feature that generic OpenStack does. It's a private cloud platform. It's very much designed to be administered by sysadmins who are familiar with the IBM ecosystem already and know how to administer complex setups with Power VM. I am merely a developer, and I have so much more respect for systems administrators now that I've had to, get some of this stuff working, because I do not understand a lot of this stuff. Made things a bit trickier than it should be. So this is what the web management interface looks like. It's a custom UI that calls into the OpenStack API. And as you can see, with all the yellow and the red on screen, I'm a great sysadmin who gets everything working perfectly. So we needed to get SysManager to use Power VC to create VMs. So we implemented a new type of VM in VM backend that you could in syzkaller that you could then use in your SysManager configuration. So as I mentioned, you support QEMU, Google Compute Engine, a couple of other platforms for various different purposes. And there's a standard set of Go interfaces that you have to implement to register your new type of VM. So we wrote a Go module. It uses Go for Cloud, which is the most popular OpenStack API client for Go. And we had to implement some hacks and workarounds to call PowerVC specific interfaces and to avoid the interfaces that PowerVC doesn't use. Ended up being about 1,300 lines of code. This code is not going upstream because it's got a bunch of elements that are very specific to our local PowerVC setup. But if someone wants to write a generic implementation for upstream OpenStack, I'd be very happy to have a chat to you about that and share what we've done. So this shows you roughly what our deployment looks like. We've got two physical servers, an x86 machine, a Power 10 machine. The x86 machine is a RHEL box that's running 3 VMs. One is a virtualized version of the HMC. One's running the PowerVC platform, and one we're using to actually run syzci. That's the only machine that's connected directly to the rest of the world. And then we've got a private network that connects that to the test system and the test system spaceboard management controller so that we can create VMs. And we've got a SAN for the storage. And under the test system, we've got a BIOS, a virtual I/O server to manage I/O. And then we've got the fuzzing VMs that syzci or sysmanager creates and manages. So we have it connected by private Ethernet just to avoid the fuzzers accidentally causing trouble. Since we set that up, we found a bunch of bugs. We've managed to triage and fix a few. None of them are quite as exciting as having the KVM crashes that I talked about earlier. But we are hoping to find more as we keep improving the setup. Here's one example, though. We hit a null pointer dereference in Arch unregister HW breakpoint, which is an architecture-specific hook that gets called when you unregister a hardware breakpoint. There was a race condition. It wasn't taking a reference on something. The task destructor was happening in parallel and destroying the task it was trying to access. Ends up in a null dereference. My colleague Ben Gray did the investigation on this and discovered actually we could just redesign the logic and then rip out the hook entirely, and then realized that we're the only architecture that uses the hook, so we can rip out the whole hook infrastructure. So minus 500 lines of code for this bug fix. Nice win. Next things we want to do, we want to enable more hardening and sanitization features that will trigger bugs more readily, such as KM-SAN. As I mentioned, Nick's been working on that. We're not in a position to upstream all of our code, but I'd love to upstream a bunch of additional changes that we've got in our private tree right now. And I'd also love to help improve the documentation a bit for the benefit of people trying to do something like this in future. We do want to report stuff to a public dashboard eventually. We did some early experiments with this, but since then we've completely torn down and rebuilt the fuzzing setup on our new Power 10 machine, and we're not quite ready to be publishing that to a public dashboard just yet. And of course, most importantly, we want to find and preferably fix more bugs. Conclusion, syzkaller is a really important tool in the kernel developers toolkit to find bugs and make Linux systems more reliable, safe, and secure. If you work on an architecture or a hardware platform that's a bit less mainstream than x86 and ARM, getting syzkaller working does require a fair bit of work to fix the various bits of the code that are platform dependent and add your own test cases and that kind of thing. And to figure out how to deploy it on your particular infrastructure. But once you do, there are almost certainly bugs in your Arch code that you're not going to find in other ways, at least until one of your customers is unlucky. This presentation isn't the full story. There's a bunch of details and additional sagas that I've skipped over or omitted for the sake of time. But if you're interested in porting syzkaller to your own platform, I'm happy to have a chat. Huge thanks to Dimitri and the other syzkaller upstream core developers. Dimitri is incredible. He's made a huge contribution to the kernel community, and he's a fantastic project maintainer. It's a great project to be a contributor on. Ben, Russell, and Alexei were the main people at IBM who helped me with getting all this set up. and many other people at IBM who helped me with various things like testing and procuring hardware and fixing the bugs that we've reported and just giving general helpful advice and moral support. I apologize sincerely to anyone I've left off the list. And with that, thank you. Any questions? We don't have time for questions?